Hi, welcome to lecture 6.5, Improper Integrals. So this is just kind of a bonus topic. It's not a kind of geometry physics thing like we've been doing, more mathy, but we're kind of all set up to do it now that we know a bunch of integrals. So the basic idea is that sometimes it seems useful and interesting to have an integral which involves infinity. So we've only so far had integrals involving like real numbers, but it's reasonable to think about infinity, right? So for example, let's look at the graph of y equals 1 over x. So it looks something like this. That's pretty bad. It looks something like this. So we've done integrals, like integrate from like 1 up to 10 or something to get this area. But it's reasonable to imagine instead integrating up to, 11 and seeing what that area is. And then maybe integrating up to 12 and seeing what that area is. And maybe 13 and seeing what that area is. And, for some functions, maybe like y equals x, it seems pretty obvious that the more to the right you integrate, you're just going to get bigger and bigger areas. And it's just going to go be infinity, right? You're going to have infinite area. What's perhaps surprising, but true and interesting, is that for a function like this one at the top, 1 over x, in fact, you will get a finite number in a specific sense. If you integrate to 10, you'll get some decimal. If you integrate to 11, you'll get some other decimal, but it'll be just a little bit bigger. And as you integrate more and more to the right, what will happen is your decimals will start sort of plateauing, right? Maybe you'll have like 0.8, and then you'll have like 0.9, and then you'll have like 0.95, then you'll have like 0.96, and then like 0.98, and maybe you integrate out to like 10 million to the right or something, and it really just looks like you're getting really closer and closer to a certain number, like to 1 or something. So in that sense, there are some integrals which, when you try to integrate to infinity, which just means go more and more to the right and see what numbers you get, that they appear to be leveling out. So because we've done 251, we have limits, we can make this precise in a useful way. But there's going to be plenty of functions which don't approach anything, like this y equals x on the bottom. So that's like one kind of what they call improper integral. So improper just basically means requires a limit to evaluate. So there's going to be infinity in there somewhere. We can also have like two-sided improper integrals. So like this middle one, I have infinity, negative infinity on the left and positive infinity on the right. That's also possible to do. And we'll see this in a minute. There's actually some cases where there's no obvious infinity, but it turns out that you will need a limit. Basically, if you graph this 1 over square root of 9 minus x squared function, what's going to happen is you'll see like negative 3 and 3. And the function will make a shape which looks something like this. And it sort of looks like a finite area, but these lines are actually like an asymptote, like going up forever. So it's like not obvious whether you would really get a finite area if you integrated from negative 3 to 3 in the same sense as we saw in this example a minute ago. But you can attempt to evaluate that as well with a limit. Okay, so let's just see the procedure. This is kind of a pretty standard procedure. So the idea is just to make what we were saying earlier a little precise, right? I said try integrating like 1 to 10, and then 1 to 11, and then 1 to 12, and 1 to 13. I'm just going to have a letter C stand for the number that I'm going to integrate to. I haven't committed yet. I have not told you what's the C I'm going to integrate to. I'm just going to integrate to some specific number C. So replace the infinity with a constant C. So let's try this. So I'm going to integrate from 1 to C, 1 over x. So I have not committed on what C is going to be. But even though I haven't committed on C, I can still do this integral, right? Like, forget about the bounds for a second. I can do the antiderivative. It's log x, right? And then I'm supposed to plug in the bounds. It's C and then 1. Okay, so let's just keep going. What's log of C? I don't know yet because I don't know what c is, so that's fine. We'll come back to that. What's log of 1? Well, you might know that log of 1 is 0. The graph of log looks like this. That's 1. So that's 0. So we just end up with log of c. So what that's saying is that if I integrate from 1 to c, the area I get is log of c. So to answer the question of do I get a finite value in the end or not, means to take the limit as c goes to infinity of my result. So this is sort of the way you want to write it. The integral from 1 to infinity, sort of by definition, this is like what you should write, is the limit as c goes to infinity of my integral when I've put the c there instead of the infinity. So this is like step 1, is breaking it up as 1 to c, and then the plan is to take a limit. We just determined that this integral was log c, so I could write limit as c goes to infinity of log c. So I just replaced the integral with the thing that I evaluated it to be, but I kept the limit sign. Okay, so then my final answer is just going to be whatever this limit is, assuming that it's a limit that I know. Now this, you have to recall stuff from Calc 1, or maybe look some step up if you haven't done it for a while, but some limits converge, meaning they become a specific number, and sometimes they don't. Diverge is a word people use. In this case, because it's log of c, we know ln of x looks like this, and so this is really just asking, do I approach a value, a y value, as log gets larger and larger? And it turns out, because of the ln function, that this actually does not converge, and you actually get infinity. So this was maybe a bad example that I started with because I was talking about how maybe it would converge. This 1 over x1 actually does not. It actually becomes an infinite value. Now this is surprising, right? 1 over x, it looks like the outputs, the y values are getting close to 0. But it turns out that when you integrate them, you actually can always make the integral as big as you want, as long as you pick c to be as big, to be large. That's actually not going to be the case for some very similar integrals. If you do y equals 1 over x squared, it turns out this will be finite. But this one will be infinite. They both have y values that go to 0. So it's not obvious just by looking at the y values. So that's pretty interesting. Let's take a look at a version of that. Here I'm going to have 1 over x to the 1.0001. Why am I doing this? Well, because if you play around, you try 1 over x, it looks like you get infinity. If you try 1 over x squared, it looks like you get a finite number. If you try 1 over x cubed, you also turn out to get a finite number. And if you try 1 over x to the 1.5, it turns out you also get a finite number. Remember, 1 over x is sort of like x to the 1. So there seems to be like some sort of pattern here. So we're just kind of going to investigate what happens when you get really close. Let's try x to the power that's really close to 1. So we're going to try 1.001. Okay, so let's just see. Our integral, by definition, the first step is to break it apart. I write limit as c goes to infinity of 1 to c. So that's the main first step, is just replace the infinity with a c. Remember, that's a placeholder for how far to the right I'm going to integrate. Now we're going to do this inside integral and then kind of evaluate the limit at the end. I think it's a good idea, just for writing math, to keep the limit sign there and just give yourself some space. And now I'm going to do the integral inside here. But just remembering that it's all still happening inside this limit. Okay, let's do this integral. Remember, this is x to the negative 1.001. So we can do power rule, right? I got to go to x to the 1 plus this, right? And I'll divide by my new number, whatever that is. So 1 plus my exponent, I'm going to get negative 0.001. And that's my new exponent as well, negative 0.001. That's the antiderivative, but I still have to plug in c and 1, right? Okay, so let's see this limit. Plug in the c, so I'm going to get c to the negative 0.001 over negative 0.001 minus 1 to the negative 0.001 over negative 0.001. So it's all copying, but it's something we can do. Okay, so now we have to actually evaluate this limit of this expression. What's happening with this c term, right? This is as c goes to infinity. So this first term, it's c to the negative 0.001. So again, this is something you could graph, but it's basically going to be like 1 over c to the 0.001, right? So it's like 1 over c to the something. If you graph this, you will see it looks something like this, and the y value is going to be approaching 0. So this is going to go to 0, which means it's all that's left is this term here. I'm going to have a positive number because the minus sign, and then 1 to the something is just 1 in the numerator. So all that's left is positive 0.001 from the denominator. 1 over that. 1 over 0.001. If we evaluate this, right, it's 1 over 1/100th or 1/1000th. And whenever we're dividing a fraction, we flip it over. So this is 1,000. So we got a fairly big number, 1,000. But that appears to be what this approaches. So we can say that the actual value of this integral, this is a number. It's not infinity. It's an actual number, 1,000. That just means that if I integrate 1 to c, and I let c get bigger and bigger, 1 to 10, 1 to 20, 1 to 30, 1 to 100, I'm going to be approaching a specific number as opposed to going to infinity, and that specific number is 1,000, is what we computed. Okay, so let's see just a couple more examples to get even more of a feel of this. This one, there's two infinities in it. There's the infinity on the left and the infinity on the right. So the idea here is going to be one of our integral rules. We can break this up into two integrals, right? I could make this the integral from negative infinity to 0 of my integrand plus the integral from 0 to infinity of my integrand. Now 0 is not super special. I could have picked any number, but 0 is usually easy because the plan is to plug it into something later, and it's usually easy to plug in 0. So now we just have to do each of these integrals sort of separately. So let's just do the first one. So I'm going to replace the infinity with a c. So I'm going to have negative c to 0, and I'm going to have my integrand. Okay. So this is an arctan. So maybe pause and think about how you can recognize that as an arctan. But one way to see it is if I rearrange this as x squared plus 4 squared. I have this formula thing where when it's x squared plus something squared, that's an arctan where the something is like my a that comes out in front, right? It's going to be 1 over 4 arctan x over 4. So we've done that one before, so I'm kind of skipping over it, but you can think about where exactly that's coming from. Let's plug in our numbers. So 1/4 arctan of 0 over 4 minus 1/4 arctan negative c over 4. Okay, so we have to maybe evaluate this. Arctan of 0. So you have to think about your trig, but you can double check or use your calculator. This is going to be 0. And we just have this part left over. So now let's take our limit. Let's do the limit as c goes to infinity of negative 1/4 arctan negative c over 4. So you have to know something about arctan in order to solve this, but if you make a graph of arctan, it will look something like this. There's a asymptote as c goes to infinity, and this asymptote is at pi over 2, and down here negative pi over 2. So as c goes to infinity, I'm doing arctan of negative c over 4. So I'm getting this value, right? Maybe this is some c, if c is 1 or something, then here's my first, negative c. And then I have a bigger negative c, and then a bigger negative c out here. And these numbers are approaching, the y values are approaching this pi over 2, or negative pi over 2. So this whole thing is negative a fourth times negative pi over 2. So again, to do the limit, you have to know something about the graph, you have to know something about arctan. So I'll let you think about that, or you can ask me about the trig stuff if you're not sure. And then this is pi over 8. Cool. So this part ends up being pi over 8. The left one, we just did the left one. If you check the right one, it will end up being the same number, I believe, because this is nice and symmetric. So we should end up with pi over 4 as like the final answer. So I'll let you maybe double check that if you're curious. But we can do each part separately is the point. This was just the left part. Okay, cool. So that's that example. Let's do one more example. So this is the one that was not obviously infinity. But the main idea here, if you graph this, it turns out you're going to have something that looks sort of like this, where this is negative 3 and this is 3. And so it's not, these are like asymptotes, so it's not super obvious if you get a finite number or not. So the idea here is, instead of imagining choosing a larger and larger c, I'm going to have c approach 3, right? I'm imagining maybe I have some c here, and then a bigger c, and then a bigger c, and then a bigger c, but I'm going to have them like approach 3. Because of the symmetry, it's negative 3 to 3, I can actually make this negative c to c, and then the plan is to take a limit as c goes to 3, and this should work out. So let's see, 1 over square root of 9 minus x squared dx. Cool, so that is an integral that we can do. Okay, so yeah, so this is an integral that we get. Let's just focus on doing the integral. Again, kind of like the previous one, this is a trig one to recognize. I'll just go ahead and tell you that this one is going to be arc sine of x over 3. So remember, if you're not sure about that, you can check out the table, or think about some of these trig subs we've done, but that ends up being arc sine of x divided by the number that's in, like 9 is 3 squared, so it's arc sine x over 3. We still have to plug in our c and our negative c, and then we're going to take a limit as c goes to 3. So let's just see arc sine of c over 3 minus arc sine of negative c over 3. So we're going to think about this a little bit. As c is approaching 3, these are approaching, like this is approaching 3 over 3, right? And this is approaching negative 3 over 3. So I'm getting closer to arc sine of 1 minus arc sine of negative 1. So as long as those are like legitimate numbers, then that's a totally fine way to think about it. Let's just try to remember like arc sine of 1 for a second, right? Arc sine of 1 is asking sine of what number, right, equals 1. And I just have to think what theta gives me a y value of 1, and it's going to be pi over 2. So this is pi over 2. And then the other one, arc sine of negative 1, sine of what gives me -1. Same story, right? I got to be down here. I'm going to need negative pi over 2. So I'll have pi over 2 minus negative pi over 2, which is pi over 2 plus pi over 2, which is pi. Nice. So this one ends up being pi, even though the graph is like this weird thing with asymptotes where it's not super obvious that you'd get a finite number. Okay, I just want to close out this section with a little bit of vocab. So this is not a huge deal, but just to have it kind of all on one page. So this word improper integral just means any integral that has infinities involved that needs a limit to evaluate. There's a couple flavors. If you're going from a to infinity, you want to do the limit as b goes to infinity of a to b. So I was using c, but remember the letters don't really matter. And the picture to have in mind is here's your starting point, and you're going off to the right. You could do the same thing going to the left if you wanted to, something like this, starting at b and then going to the left. So I'm going all the way from negative infinity up to my point b. So I can write the limit as a goes to negative infinity of my integral. It would also be fine to write limit as a goes to infinity of negative a, right? As long as the sign works out, that's fine. We did this example. If you have to go from negative infinity to infinity, you could just do the left one plus the right one, and you could pick any in-between number. We picked 0 in our examples. In all these cases, the vocab word is that the integrals converge, and if they don't, they diverge. So converge means we converge, we settle upon a finite real value. Diverge is we don't settle, we explode to infinity. So you don't need to know those words, but it's nice shorthand words. And then the last example we did was kind of this situation where I can have the limit going to a number that's not infinity. That's fine. So I'm going to write from a to b, but like I can't evaluate it at a because there's an asymptote here, but I can do the limit as c approaches a from the right of this integral. So I'm kind of scooping closer and closer to the asymptote. Sometimes you get a finite number when you do that, sometimes you don't. So number 2 here is the same thing, just kind of coming from the left side. Number 3, sometimes you can break it up into these two cases, kind of sandwiching the middle like that. Okay, so that's it for improper integrals. Thanks for watching, and I'll see you around.